Hello everyone, welcome back to my YouTube channel Unfog with Dr. Atahar Parveen. This lecture will be the second part of the chapter Electromagnetic Radiation. In our first lecture, we discussed all about electromagnetic radiations, their examples, properties, uses, and what were the different electromagnetic radiations, and also we discussed about the electromagnetic spectrum. In this lecture, let us discuss all about photoelectric effect, its experimental facts, observations, and how did Einstein explain this photoelectric effect and what are the applications of photoelectric effect, and also let us solve many of the questions, the MCQs, which are expected from this chapter. If you have not watched the first lecture, please go and watch the first lecture. I will give you the link in the description. In the first lecture, we were talking about photons. We gave little bit introduction about photon, then we moved on to electromagnetic radiation. Now in this lecture, we will again start the discussion with the photon itself. In that lecture, we told that photon is a bundle of energy or a packet of energy. Or in simple words, we told that photon is a single wave. We can relate to photon as a single wave, we told there. Now we also told that the energy of a photon, E is equals to h nu. We are talking about the wave nature of light, remember. When we are telling about photon, we are talking about the wave nature of light. When we are telling that the energy of photon is equals to h nu, that means we are talking about the wave of light. Nu is the frequency, right? That frequency will be there only for a wave, not for a particle. So we told that E is equals to h nu in the previous lecture. We also told that nu is equal to 1 upon lambda, or nu, the frequency is inversely proportional to the wavelength of a wave. Here, if I remove the proportionality constant, I can introduce this term C, which is the speed of light of electromagnetic wave. Okay, let me repeat it for you all. In E is equals to h nu, E is the energy of the photon, h is the Planck's constant. We also told about the value of the Planck's constant in the previous video. That is very important. And then nu is the frequency of radiation or the frequency of the photon. And this frequency is inversely proportional to the wavelength of the photon. If I remove this proportionality symbol, then I can include this constant speed of light C. This will be equal to 3 into 10 raised to 8 meters per second. Okay. So I hope you got it. Just remember E is equals to h nu and this in turn is equals to hc upon lambda. Now let's talk more about photons. What are the properties of photons? Because unless and until we know the properties of photons, we cannot relate to what we call as photoelectric effect. Now photons travel at speed of light, which is c, and this speed will be there even in vacuum. Okay, this speed is equal to 3 into 10 raised to 8 meters per second, as we are telling it oftenly. Next property of photon is very interesting. It is that the photon has zero rest mass. Zero rest mass means if it is at rest, then it is not having any mass. If the photon is at rest, then it is not having any mass. That means photon cannot exist at rest. It can exist only if it is moving. Obviously, photon is light, right? If it is moving only, you can know that there is light. Or else it is not existing at all. Okay? So, photon has zero rest mass. Third property of a photon. The kinetic mass of a photon m is equal to E upon c square or h upon c lambda. For this, I will have to explain you a bit. Let us go back to our class again. We told there E is equal to h nu, right? That was for a wave nature of light. Now, what will be the equation of the energy for particle nature of light? It will be the well-known E is equal to mc square. Okay? So, E is equals to mc square will give you the energy of the light when it is behaving as a particle. And when it is behaving as a wave, we told it, right? E is equal to h nu. Now, if I relate the right hand side, mc square and h nu for energy, then I can relate this m and the frequency, the mass and the frequency of the wave. Okay. And also we told that E is equals to hc upon lambda, right? Because nu is inversely proportional to lambda. That is the frequency of the wave is inversely proportional to the wavelength. Then we introduce this term speed of light, that is c. Now I can equate mc square and hc upon lambda, right? Mc square will be equal to hc upon lambda. Now I can say that m is equals to h upon c lambda because there is c square in the numerator. Here c in the numerator. Then if I divide, then 1c will get cancelled and it will be in the denominator. So I can say that m will be equal to h upon c lambda. So this is your kinetic mass of a photon. Either you say E is equal to mc square or m is equals to E upon c square, or you say m is equals to h upon c lambda. Now this h upon lambda is there, no? If I remove this constant, there is one term h upon lambda, right, in the right hand side. This h upon lambda is nothing but the momentum of the photon. This is also relating to the particle nature of the light. If you see about dual nature, the de Broglie wavelength, that comes into picture here. The momentum of this photon will be equal to h upon lambda, where lambda will be the de Broglie wavelength. If you have attended my GPSTR classes, the dual nature part, then you will be knowing. But still, I will give you the link in the description. You can go and watch there. This is a very, very interesting topic actually. This is known as modern physics, the quantum mechanics. It really gives goosebumps when I read this part of physics every time, because this is really very interesting. No one can imagine that light is behaving as a wave and also as a particle. Think how great those people should be. De Broglie, Einstein and Planck. I really don't understand what type of minds they should be having. Really great. Okay. So coming back, the fourth property of the photon is that the momentum of the photon is equals to h upon lambda. Or I can also say that it is equal to E upon C, because E is equals to hc upon lambda, right? So here if you remember these four equations in the right hand side, E is equals to mc square, E is equals to h nu, E is equals to hc upon lambda, and P is equals to h upon lambda. If you remember these four equations, no, then you can say entire properties of photons. You can purely describe the properties of photons based on these four equations only. Okay. Next, fifth property of the photon is that the photons travel in a straight line. Obviously, we are studying from school, right? Light has a rectilinear propagation. It moves in a straight line. We know it. Next, point 6 is that energy of a photon, it depends upon frequency of the photon. So the energy of the photon does not change when photon travels from one medium to another, because E is equals to h nu, right? E is equals to h nu. Energy is depending only on the frequency. Unless and until there is no change in frequency, there is no change in energy. So whatever the medium is there, no problem at all. Energy will be same. Next point is that wavelength of the photon changes in different media. So velocity of a photon is different in different media. We know it, right? Frequency is inversely proportional to wavelength. And this wavelength is related to the speed of the photon also. V is equals to f lambda, right? We told. Now that lambda, if it is changing, means there is some change in the medium. Then only it is changing. Then if it is changing, means the velocity of the photon will also change. So the moral of the story is that if the medium is changing, if the photon is traveling in different medium, its energy will not change, but its velocity will change. Okay, that is because of wavelength. Next is that photons are electrically neutral. Obviously, they are neutral. That's the reason they will not bend also. They will not deviate among magnetic and electric fields. And also photons, they may show diffraction under given conditions. Not only diffraction, they may show interference also. But you have to have some given conditions. Under particular conditions, they will show you all the optical properties. Okay. So these were the properties of photons. Any of the question may be asked in any twisted way. That's why I am giving you. This is very important. Unless and until we understand the properties of photons, we cannot understand the photoelectric effect. Now let's talk about photoelectric effect. Imagine that there is some metal block and you are putting light on it. A ray of light, or many of the photons, they are getting incident on it. Then you have to imagine what will happen. You may feel that light is falling, nothing will happen. But that is wrong. That is not going to happen. If light falls on a metal, then electrons will be ejected from that metal surface. Those electrons, they gain energy from this light. From now onwards, every time I will address light as photon. Okay. That photon's energy is absorbed by the electrons on the surface of the metal, and with that energy, those electrons come out of the metal block. This is known as photoelectric effect. But this will not happen all the time. This will happen under particular conditions. These electrons, they will need some minimum energy. That energy they are gaining from the photon. Okay, this minimum energy, if they have, then only those electrons will escape from the metal surface. And this energy is known as work function. The symbol is phi naught. And this work function, it will have a unit EV, electron volt. When I say that this work function is the minimum energy required for an electron to escape from the metal surface, I mean to say that only those photons with energy greater than work function phi naught will result in emission of electrons. If the photon will have energy less than the work function phi naught, then the emission of electrons is not possible. Okay, because those electrons, they are gaining energy from photons and they are getting ejected from the metal block, right? Now this electron volt, this is the energy gained by an electron when accelerated by a potential difference. That means if you are connecting some battery or something like that, then you can relate it to potential difference. And usually this electron volt, this can be converted into joule also because it is energy, right? So this 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. This is the important value you have to remember. Every time you want to convert electron volt into joule, you have to use this value 1.6 into 10 raised to minus 19 joules. Okay. Now let's go deeper into photoelectric effect. As I told you, it is the phenomenon of emission of electrons from mainly metal surfaces which are exposed to light energy. This light energy, it could be X-rays, gamma rays, UV rays, visible light and even infrared rays. We are talking about the electromagnetic radiations now, isn't it? But the only condition is that this light should be of suitable frequency. For a particular frequency only photoelectric effect occurs. And the electrons which are emitted by this photoelectric effect, they are called as photoelectrons. And these electrons, when they are emitting, means they are constituting some current, right? So these current formed by the photoelectrons is known as photoelectric current. Now this photoelectric current is the hero of this photoelectric effect. All the applications of photoelectric effect are all based on this photoelectric current, because this is the speciality of photoelectric effect. The emitted electrons, they are forming the photoelectric current. Okay. Now one important note is that not only metals, even non-metals can show photoelectric effect. Even liquids and gases, they also can show photoelectric effect, but to a limited extent. If you want some dominating photoelectric effect, then only the metals are the right materials and one particular frequency light also should be incident on it. Then only photoelectrons will be ejected. For example, if you have this UV light which is incident on the metals, then you can see photoelectrons. But if you have visible light on metals other than alkali metals, then you will not have photoelectrons. No electrons will be ejected. But then again, if you have some particular visible light which is focused on only alkali metals, then again you can have photoelectrons ejected. Now you may be thinking that what is this, ma'am is confusing us. So this is, I am giving you intro. I will talk more on it and by the end of this lecture you will be very happy to understand photoelectric effect. I will give you the answers why all this is happening. Okay. Now this photoelectric effect, basically this was studied by Hertz. Actually before Hertz also people were there, Halvox and Leonard. Okay, before 1887 also this Halvox and Leonard, they observed photoelectric effect. But main work of this photoelectric effect, the observations and the experiments, this all was done by the well-known Hertz in 1887. Now before starting the discussion on the experimental studies of photoelectric effect, I want to have a talk with you all regarding some photons. What all may photons do? Now we know about this wave, right? Even in our last lecture also we were discussing about this wave. We told that it has crest and it has troughs and the distance between them is wavelength. Now let's see these two types of waves. This is one wave, this is another wave. In the first wave you can see that the wavelength is short. In the second wave the wavelength is long. Why? Because in the first wave frequency is high and frequency is inversely proportional to wavelength. That's why high frequency means that wave will have short wavelength. And in the second case, the wavelength is large, the long wavelength is there. That means the frequency will be low. For the same reason, frequency is inversely proportional to wavelength. Now if I see the amplitude, here the amplitude A is there, no? This is changing or not? Yes, this is changing. If you have high frequency, then the amplitude will be high. If you have low frequency, then your amplitude will be low. Why? Because we told that nu is equal to C upon lambda. Remember, nu is equal to C upon lambda, and your energy is also related to the frequency. Energy is equal to H into nu. That means your high frequency implies that that wave is having high energy. Your low frequency means that wave is having low energy. Okay. Now, we also know about a certain parameter known as intensity. What is intensity? Intensity means number of photons. If intensity is increasing means you are telling that the photons number is increasing. Increasing number of photons means increase in intensity. See, for example, if this is a metal block, now I am giving only one light ray, I am putting incident on that metal, then I am getting one electron ejected. If I want to increase the intensity of the light ray, what I will do? I will give more light rays, right? So now I am increasing the light waves. This increase in light waves is nothing but increase in intensity, which in turn is increasing the number of electrons ejected. That means more photoelectrons are ejected with a more intensity. Now let me give one simple summary. See, when I talk about intensity, that is if the number of photons are increasing, what all will happen? If intensity is increasing means number of photons are increasing. Intensity is increasing means number of emitted electrons are also increasing. And intensity is increasing means photoelectric current is also increasing. Isn't it? Increase in intensity means number of photons are increasing. Increasing intensity means number of emitted electrons are increasing. And this number of emitted electrons will constitute a current which we call photoelectric current. Because they are increasing, current will also increase. So intensity plays a major role here. Now I ask you one question. Does the kinetic energy change? No, it will not change. This you should not get confused here. If intensity is increasing, kinetic energy of electrons will not change. Here I will give you one simple example. This, I think men will relate to this example. When in your childhood you used to play that game, right? Especially in Karnataka we play it. That marbles on the road you play with your friends, right? In your childhood you must have played. You gather many marbles on the road. You make one circle and you put marbles. Then you beat one. Each one of you will beat one marble in that group. Isn't it? What will happen? You beat one marble, marble will come out. Isn't it? Now you imagine this photon as that marble. And those group of marbles are there. Now imagine them as electrons on the surface of the metal. Now I can give you nice explanation on this. See, if you are beating one marble means maybe one or two marbles may come out because they are together. But if you beat with many marbles at a time, many marbles will come out, isn't it? That means you are changing the intensity. You are increasing the intensity of the marbles. Therefore, those marbles which are coming out, they are becoming many. Many marbles are coming out. But are you changing the speed of the marbles which are coming out? No. Kinetic energy is related to the speed, right? If you want to change the speed of the marbles coming out, then you don't need to use many marbles to beat them. You can use only one marble and you can beat it very fastly. That means you can change the frequency of that marble. You can increase the frequency of that marble. If you beat that very fastly, then one electron or one marble from that rod, it will come out very fastly. Then you are changing the kinetic energy. Okay. So you are not changing the kinetic energy by the intensity of the photon here. You will change the kinetic energy by the change in frequency of the photon here. Okay. If you all have understood, well and good. I will talk on this more. If you have not understood, you will understand it. Don't worry. Please watch the full lecture patiently. Now, what this Hertz did is, he conducted one experiment. In that experiment, this was to study the photoelectric effect. This is an experiment for photoelectric effect. One glass evacuated tube was taken. In that one window was made. That window was from cords. It was made from cords. Then two plates were attached. One plate was C and the other plate was A. The cathode and the anode. Now this plate C, it is a emitter plate. It is a photosensitive plate. Why it is becoming emitter means your light, it is getting incident on this plate. Once the light falls on this metal plate, what will happen? Electrons will get ejected, right? These electrons are being collected at A. That's why this A becomes the collector plate. Okay, C is the emitter plate and A is the collector plate. Now you can see that before I incident this light on this photosensitive plate or the emitter plate, before that the circuit will be incomplete, right? Where is the connection? You can see that this C is attached to a rheostat, the commutator, the microampere ammeter, then voltmeter and a battery. A is also attached here to the rheostat, isn't it? But are C and A connected to each other with any wire? No, there is no circuit, right? But when the light falls on this photosensitive plate, the emitter plate, electrons are emitted and then they are getting collected at the collector plate A, which forms the flow-in current. So your circuit becomes complete here. These electrons which are moving from C to A, they form a virtual wire, isn't it? That's the reason why your circuit gets completed here. So this current is known as photocurrent. You can measure this current with the ammeter because this will be a very less current. That's why we are connecting a microammeter. It will not be a milliampere. It will be a microampere ammeter. This will be very less current. So all the play in this photoelectric effect is about that photocurrent. Okay. Now people also have graphs and all that are not very important, but I'll give you a glance on all that. Now with this experiment, there were few observations, the conclusions of the experiment. What were they? First is that photoelectric effect depends on intensity of photons. We can plot the graph also. You can see that the photoelectric current is linearly proportional to the intensity of light. Here I have put this diagram here to make you all understand it easily. See here in the first case, if I am incidenting with one torch, if I am incidenting a light ray or photons, then 3 of the electrons are coming out. If I will use 2, then 6 may come out. But am I changing the kinetic energy of these electrons? No, I am not changing the kinetic energy of electrons. I am just changing the number of photoelectrons which are getting ejected. So this is how intensity is related. Okay, and this energy is independent of intensity. Which energy? The kinetic energy. It is independent of intensity because intensity is just increasing the number of photoelectrons. It is not increasing the energy. Now, as I told you, this effect of potential on photoelectric current, it will be a straight line actually because you are connecting a battery, right? And this maximum kinetic energy of the electrons which are getting ejected should be equal to E into V naught. E is the electron charge, 1.6 into 10 raised to minus 19 coulomb. But this V naught is the stopping potential. If you plot this photocurrent, no, with collector plate and retarding potential, means that is the negative potential, you can find this stopping potential. But I am not talking on it because no, this is not important. So much deeper they will not go for HSTR and KREIS. They will ask all the general questions. They will not go so much deeper. Okay. These are all high level questions. So don't get into trouble by going so much deeper. Just if you know the gist, if you know the general part of the photoelectric effect, that is more than important for you all. So first observation was that photoelectric effect depends on intensity. Yes, it depends on intensity, but energy is independent of intensity. But then what will change the energy? It should be frequency, right? It should be frequency. Remember the example of the marbles. The frequency will change the energy. This was the second observation. See, if you have low frequency light, then no electrons were ejected. See, if you have low frequency light, no photoelectrons were ejected. So this is related to your threshold frequency nu naught. Nu naught means that frequency or the threshold frequency wherein greater than this nu naught only photoelectrons will be ejected. If the frequency of the light incident on the metal is less than this threshold frequency, then the photoelectrons will not be ejected. So if you have high frequency, then photoelectrons will be ejected with higher kinetic energy. Okay. Here, kinetic energy of photoelectrons, it will increase linearly with increase in frequency. This wavelength, the threshold wavelength lambda naught comes into picture here. This lambda naught is equals to C upon nu naught. We know that lambda is equals to C upon nu, right? It is inversely proportional. So that threshold frequency and threshold wavelength comes into picture here. Now when I say that the high frequency light ejects electron means change in frequency means change in wavelength. Change in wavelength means change in color of the light. Isn't it? Remember the spectrum, the visible light spectrum. We have waveguides, right? You can see that the wavelength increases from the violet to the red. Low the wavelength, high the frequency. High the wavelength, low the frequency. So if you have high wavelength, that means low frequency, no photoelectrons will be ejected. If you have low wavelength of the light incident on that metal, then you have high frequency and photoelectrons will be ejected with more kinetic energy. See, for example, here I have metal block and I am putting red light on it. Red light is having high wavelength, low frequency, no photoelectrons, isn't it? Now if I incident a little bit lower wavelength light, that is green maybe, I will have photoelectrons because green is having higher frequency. Now the most highest frequency light, that is the blue color, then I will have electrons which are having more kinetic energy. Okay, these were the observations of photoelectric effect. The two main observations, that intensity is dependent on the number of photoelectrons ejected and frequency of the incident light is dependent on the kinetic energy of the photoelectrons ejected. Now this photoelectric effect, because of the photoelectric current, I told you, right, that photoelectric current will give many applications of photoelectric effect. One of the best is this photocell. Same process happens here also. You give the light and then electrons, they get collected at the collector region. They are emitted from the emitter plate and they are collected in the collector plate. And then photoelectric current will flow and then you can have a current in the photocell. Now this photocell, it has many practical applications. Along with this, there are many other practical applications of photoelectric effect. For example, it is used in electronic ignition circuits. Then it is used in measuring intensity of light, in research, in laboratory. Many people use it there. And then it is used in automatic door opener. You must have seen in this big malls nowadays, no? Malls or supermarkets. You don't need to touch the gate. You just enter the gate, it will open by itself. There is some sensor, right? Here that photoelectric effect application is used. What happens? No, photoelectric current is flowing. When you go in between, no, when you go near that photoelectric current, it will get disturbed. When that photoelectric current is disturbed, what will happen? There is one sensor which will trigger that motor and then the door will open by itself. Once you go inside, again, if no one is coming in the way, again the door will close by itself. So this is the application of photoelectric effect. They can use in this auditorium. They can count people. How many disturbances are created in the photoelectric current? So many people are there in the auditorium. It is like that. And even traffic police also, they catch this traffic defaulters. At that time when their signal is on, right, the red signal is there, if still people are going, means they can count the number of people. They can see who is disturbing the photoelectric current and then they can catch them. And very important application is the burglar and fire alarms. They have these sensors. If that photoelectric current is getting disturbed by something, then that sensor will trigger and that alarms will ring. Okay, so these are all the applications of photoelectric effect. Now finally, by the observations of this photoelectric effect experiment, we can have the laws of photoelectric emission. The first law is that emission of electrons is possible only when sufficient amount of energy is incident. What is that sufficient amount of energy? That is work function phi naught. Then more light will eject more electrons with same kinetic energy. That means energy is independent of intensity. Remember the marbles example? That you can imagine if you are not understanding what I am trying to tell. Next law is that low frequency means no ejection of electrons. Only high frequency electrons will eject electrons with more kinetic energy. So frequency of the incident light is changing the kinetic energy of the photoelectrons. And last one. The instantaneous process is happening here in photoelectric effect. The photoelectric emission is instantaneous. See, just remember again the marble example. When you beat the marble to the group of marbles, does the marble take time? It will not take time, right? It will just, as soon as it will hit, it will come out. That only happens here also, because we are treating photons as particles, right? When one particle is beating the other particle, it will suddenly come out. It will not take any time. There is no time lag. If there is time lag also, it will be so less that it will be negligible. It will be around 10 raised to minus seconds, means 0.009 times 0.1. So much small time is there. That's why we can directly say that it's an instantaneous process without any time lag. After the observations and all the conclusions, Einstein explained why this is happening and how this is happening. He gave one equation, photoelectric equation. It is very well known equation. Let's talk on it. When a photon of energy h nu falls on the metal surface, energy is h nu, right? So when this photon falls on the metal surface, this energy of the photon is absorbed by the electron on the metal surface, and then after absorption, this energy it is used in two ways. The electron uses this energy in two ways. What is the first use? One part of energy it is used to overcome the surface barrier. It will use to come out of the metal surface. Okay, this energy we call as work function. This is also E is equals to h nu only. But we are giving that symbol phi naught, right? So here for frequency nu we will write nu naught. E is equals to h nu naught. Then the remaining part, which is remaining no energy, that is used in giving velocity to that emitted photoelectron. That's the reason why we are telling that if more energy we want from the photoelectron, then we have to give more energy. The photon. If more energy for the photon means energy is directly related to frequency, right? That's why E is equals to h nu. If the more frequency light is given, more kinetic energy will be there for the photoelectron. Okay. Now this is all was told by Einstein. Here you can see the depiction. One h nu we give, then we have this photoelectron with kinetic energy half mv square. According to law of conservation of energy, Einstein then gave this equation of photoelectric effect. He told that E is equal to whatever energy is there for the photoelectron, that is equal to these two energies. First is the work function plus the kinetic energy. Work function is h nu naught, right? Then the kinetic energy half mv square. And E is h nu, which is in the left hand side. With this we can say that the kinetic energy of the photoelectron is equal to h into nu minus nu naught. Okay, this is an important formula. You have to remember it. Now one question came in your HSTR question paper of 2015. The question was that which one of the following is the Einstein's photoelectric equation? E is equals to h nu naught plus half mv square. Now you can relate to it, right? Now let's talk about many expected questions from this part. First question is that which photon is more energetic, a red one or a violet one? Obviously, because E is equals to h nu and E is equals to hc upon lambda, it should be violet. Remember Vibgoi, lower the wavelength, higher the frequency. Higher the frequency, more is the energy. Okay. Next question, if the wavelength of electromagnetic radiation is doubled, what will happen to the energy of photons? E is equals to hc upon lambda, right? If wavelength gets doubled means energy, it should be halved because it is inversely proportional. You can write it and see again. You will let me know in the comment section also whether you are getting this half or no. Next question, which radiations will be most effective for the emission of electrons from a metallic surface? It should be ultraviolet because it is having the least wavelength. Least wavelength means highest frequency. Highest frequency means highest energy. Highest energy means more emission of photoelectrons. Okay. Next question, give the unit of work function. It is electron volt. Next question, what is the time lag between the incidence of photons and the ejection of photoelectrons? We were talking about this, right? It is less than 10 raised to minus 9 seconds. Which device works on the principle of photoelectric effect? Not only this emission cell, junction diode, voltaic cell, even the photo cell, all these, wherever the photos are there, no, they are all photoelectric effect only. So all are correct. Next, the photon, it is having no charge. Okay, it is neutral. Then the minimum energy required to remove an electron is called, of course, it is called work function phi naught, and the unit is EV. Remember? Okay. And the energy will be E. It is equal to h nu naught. So this was a little bit conceptual based class. That's why I tried to explain you the best way possible. I used examples also, and many of you must be having idea also about this. Many of you must have been forgotten, but still I hope that this class will help you all in understanding the photoelectric effect, which is a very important topic. Even after you get jobs, or even if you are teachers now, it is very important for you all to teach children properly the manner they understand. Simply giving the definitions and all will not help. Being a person from science, being a science teacher, it is very important for us to teach the children of our class the concepts. Giving just definitions will not help. We need to give them examples and make them understand. Try to talk to them. Then only we can make physics easy. Okay. So I hope that this class will help you. And if you all have any problem, please let me know in the comment section. And also do like, share and subscribe to my channel. Please watch the full video, because see, I am working so much hard. You all are not watching the full video. I get upset. So please don't do that. Have patience and watch the full video lecture. Okay. Okay. Thank you. All the best.